13B, exercise 13B is conditional probability and independent events. Now let's just recap. I mentioned about independent events and dependent events yesterday. Can someone tell me again the difference between mutually exclusive and independent events in your own words for me? Let's start off with Richie. What is mutually exclusive?
Like where one event has no correlation to the other, so they don't have an intersection.
Good. Probability or the chance of an intersection is nothing. So A intersection B is equal to 0. Whatever the two events are, they're totally unrelated. There's no chance of them occurring at the same time. Okay? Mutually exclusive means that. But then what's the difference between mutually exclusive and independent events? Let's go with Aaron.
An independent event is one where no effect on the two events that are like whatever happens in A, it doesn't matter. And it doesn't affect what happens in B.
That is correct. So how's that different to mutually exclusive? Because you're right in the sense that if you had A, not A, and then you get B, not B, B, not B, yes, you're right that the chances of A does not affect the chances of B. So getting B is just B. Probability of B is just probability. Blech. Probability of B is just the probability of B. It's not probability of B, but depends on A. Probability B is still the probability of B. That's what we're saying when they're independent, right? So that's what you're saying. But I asked, what is the difference between mutually exclusive and independent events? So how do we tell? They're linked by one rule. They're linked by one rule, and that's the difference between the two. And this is how you show in an exam question when they say show that it's mutually exclusive or show the independent events. This is the rule that separates it. You told me the theory. I want to know the rule that separates the two. What is it? Let's go with someone else. Trent.
I have no idea.
You have no idea. Let's go with Anna. Good. Which equals to 0. So probability of A intersection B is 0. And independent events, which is? How do you show if something's independent? Yes, it was along those lines. Remember that I had two lines that mentioned that linked the intersection. Yes, you're right. Yes, Aaron, again.
The A intersection B over the conditional event.
No, that's talking about conditional. I'm talking about independent events. Ben?
Was it just probability of A intersection B is probably A?
That's it. So we're just going back to what you were saying here. You said the chances of A does not affect the chances of B. So now moving on an extra step. Now you say what's the chance of getting A and B? Okay, so the chances of getting A and B at the same time. What you would say is, well, probability, I'm going to do it here, probability of A and B occurring is equal to, and normally how we'd do it is we'd say multiply the branches, which is probability of A times probability of B. Now here's the difference between the two, and this is what I wrote yesterday, so I'm going to write in blue. If they are independent, okay, that means probability of A multiplied to, now the second branch, this branch here, normally it would be probability of B given that there is an A, because that's the second term, right? If A was the first one, then B obviously depends on A. Okay, so this is the scenario that B will depend on A, but in independent events, we just said B given A is the same thing as B. That's the theory that Aaron mentioned. Now I'm taking it a step further, then how do you show it? The showing part is right here. If that's the theory, then we're now saying because it's independent, it doesn't matter. B given A doesn't matter because A doesn't affect it. So therefore, it's the same thing as saying probability of B. And therefore, you put it together and you say probability of A times probability of B will give me the intersection. That's how you prove it in the exam. If they asked you to show that these two events are independent, you will find your way through a list, through a sample space, so you can find out probability of A intersection B. But then they would have gave you A and B already, and you have to multiply those two to check that they're both the same. If they're both the same, then you can say, therefore, they are independent. An example would be this. I'll give you an example which we all know. Let's say rolling a die, flipping a coin. You get heads, tails, heads, tails, heads, and tails, right? If I asked you to write the sample space, you said out of 2, flipping the coin twice, you get heads on the first go, heads on the second go. You can get H, T, T, H, and T, T. Now if I asked you what's the chances of getting H and T at the same time, so you didn't have to calculate much here. You can just say, oh, well, there's H and T here, and there's H and T here. You would say there's 2 out of the 4. And you'd say that's half. Agreed? Okay, so you'd say, yeah, that's the chances. But unless I asked, what's the chance of getting H first and then T, then you would have said probability of H and T. So H first, then T, then you would say that's a quarter. Agreed? But that's depending on the question. So let's just say it was H and T. H and T, that would have been half. Now, how do you prove? Let's go with probability of half, which is getting H. Chances of getting H again. Normally, it would have been probability of H intersection T, okay, would be probability of H multiplied to probability of T given that H had occurred. But because it's independent, in our case we know that flipping coins are independent, then technically probability of getting tails doesn't matter about H. It would just be probability of getting tails. So here we go. In this line here, I would be writing probability of H multiplied to probability of getting T, because it doesn't matter about H. And the chances of getting H is half, multiplied to chance of getting T is also half. That gives me a quarter. Okay? And that's saying this is equal to this. The chances of getting H first and then tails, because that's the branch I went with. H first, then tails. Okay? They're both the same. Therefore, they're independent. Okay? That's how you'd show that. But otherwise, if they're not the same, then this line stays true, in the sense that T does depend on H. That's why the intersections are different. Okay? So what's the difference between mutually exclusive and independent events? Mutually exclusive is just the fact that intersection is always 0. Whereas independent's a theory. And the theory can only be proven if this is true. If this part is true. So this times this equals the intersection. That means this has no effect on H, or H has no effect on T. Does that make sense? Yeah? Okay, cool. So now, with that understanding, now we'll lead to conditional probabilities. So we learned independent events, the theoretical part. Now we're going to conditional. And another way of saying conditional is really dependent. So you either have independent or you have dependent. Now dependent would mean that if I were to do the HT, 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 and I said find the probability of H and T, so getting H first on the first go, T on the second go, you would say the probability is probability of H times the probability of T given H. This is dependency, because tails will now actually depend on H. And this might be a biased coin or something. That's why it depends on what you get for the first one. I don't know. Maybe it's a biased coin. Okay? So this is what I'm trying to find out. Now, if it is dependency, see, if I rearrange this equation, this is what, sorry, not red. This is what Aaron was saying before, the formula that I gave to you yesterday. If you divide both sides by probability of H, this is your formula for probability given H is equal to probability of H intersection T over probability of H. This is where you learnt it last year. That was the rule that you got last year. So if I gave you the rule you had last year was probability of A given B is equal to probability of A intersection B divided by probability of B. Because B's the affecting one. B is what is affecting your issue. So similarly over here, when I said chances of T, depending on H, it's out of H, depending on what H is. If H does affect it, this is the issue. Okay? Same thing, this is the rule that you got last year where you said A given B, and it's out of B because B affects A. Okay? If you change this and you say probability A is independent of B, then technically B doesn't affect it. So probability A equals to probability A intersection B divided by probability of B. If you rearrange that, then you get the independent formula rule. Okay? So this rule here on the top here that I have in blue, that I've highlighted, They gave that a name last year, and they called that the multiplication rule. So there are two rules you learned yesterday. There was addition rule for the union, and for the intersection, that's the rule. This is the rule for multiplying. When you're going across branch from one branch to the other, you multiply, so they call it the multiplication rule. When you're unioning, this means that when you're grouping this branch with this branch, so you add them. Okay, so that's the difference between multiplying and adding. But that's what exercise B is. Okay, 13B is talking a lot more about this theory. So the better you understand what independent events are, mutually exclusive, then conditional probability makes a lot of sense. Okay, because it's just a dependency. So it's more of the questioning, depending on the question. So if they said, you know, the chances of, I don't know, let's say Susie playing basketball and winning depends on whether she won the last game or not. Okay, or if she said the chances of her winning a game depends if she plays at home or she plays overseas. See, that all depends. That's a conditional. That's a condition problem. Whereas if it's independence, they normally tell you at the end of the question, they'll say, given that these two are independent events, then you have to know that you're going with this, with that probability. Okay? So that's the only difference that you have to understand between the two. Cool? Now let's do an example. So that was the rule from last year. So if I just delete everything, so you can see this is what you learned last year. That's the multiplication rule. Just rearrange it. It's all by theory, depending on that. So A given B. Okay? Now let's do an example. Let's do an example. This is kind of math. I'm going to move away from this. Here we go. Let's go with this example. This one will really illustrate the idea of dependency or given. Okay? I want you to look at this. You've got 1,000 drivers. Okay? 1,000 drivers were questioned and classified according to age and number of accidents. Okay, so you've got age and you've got number of accidents. So you're either less than 30, you're older than 30. Okay? Or 30 or more. Okay, so less than 30 or 30 or more, you either have been in one accident or more than one. Okay, so for the people who are under 30 and having only one accident, it's 130. Okay, if I read this whole entire table, this tells me there are 1,000 drivers in total. Okay, 400 of them are older than 30 or 30, and 600 of them are less than 30. Out of the 1,000 drivers, only 300 of them had one accident. 700 of them had more than one accident. Okay, so that's what I'm illustrating in this table so far. So this is your Carnot maps. Okay. Now here's the question: a driver selected at random. So I randomly select a driver out of 1,000. And it says, given that the selected driver. Okay, so I'm giving a condition already. I'm telling you, what if the person I chose is less than 30 already? Okay, so out of 1,000, what if I already gave you a hint? I said, I've sort of randomly selected someone, but I already know this person that I chose is less than 30. How does that change the problem? Why is that different? Yeah, because it changes the group. Because initially it was 1,000. Now 1,000 is mixed up with people who are less than 30 and people who are greater than 30. But when I tell you that given that I've selected someone who is already less than 30, I know these 400 people don't fit in that random person I chose. It's out of the 600. So out of these 600 people, those people are less than 30. So out of this sample, I'm now saying, what is the chances? What's the probability that you had more than one accident? So you would say, well, out of these 600 people who are already less than 30, chances of one accident is 470. So if I ask you what's the chances, you would say it's 470 people out of 600. Does that make sense? So this is what I'm doing logically with you. If you weren't to use logic to say the answer is 47 on 60, then what you would do is you would say this. You would do probability of, you're trying to find the chances of more than one accident. So I'll do more than one accident. Given that you are less than 30 is equal to, using your formula that you had on the last page, you would say it's the probability of greater than one accident, more than one accident, intersect less than 30, divided by, it's depending on what you're affecting. Okay, so what is it dependent on? It's dependent on being less than 30. Okay, that's what you would have done. Now, how do you find the intersection? If I were to answer this, what's the chances of more than one accident and less than 30? Okay, what's the chances for both of those two to occur? Less than 30, more than one accident is 470. 470 people out of how many people in total? 1,000. That's the chances. If I asked you what's the chances of being less than 30 and having more than one accident, you would have said it's 470 out of 1,000 people. True? And then if I said, well, how do you find the chances of someone less than 30? You would say less than 30, well, there's 600 out of 1,000. And you would have done this. You would have said it's 470 out of 1,000 divided by 600 of 1,000. Well, what naturally happens here is 470 out of 1,000 divided by 600 out of 1,000. You know when you're dividing fractions, do the reciprocal, and you get 470 over 1,000 multiplied to 1,000 over 600, which ends up being the same as what I just told you before. So I use logic to answer the question, or you can use the formula algebraically to answer the question. But what I want you to understand is the logic. If you get the logic, the conditional probability is not hard. So what you learned last year shouldn't have been hard. So after all the basic probabilities set notations last year, the only new thing you learned last year, year 11, was this theory. Okay, so knowing the difference between independent events and conditional. Cool, because you're going to be using this, and it's likely, if I had to guess, if I had to make a question hardened probability for the end of the year, it would be a conditional problem. So you'll be doing all these other new chapters. You'll be doing chapter 14, continuous and discrete probabilities, normal distribution or binomial distribution. I can use conditional and apply it in that. That's when it gets hard. That's when you think it's hard. It's not hard. It's the better you understand the logic, the easier it is to answer the question. But chapter 13 is revising all the basic skills that you need. Then you apply chapter 13, 14, 15, 16, 17. Okay, so the better you understand 13, the easier it is to do 14, 15, 16, 17. Does that make sense? Cool. All right, let's do another problem. So that's just the answers there to show you it's 47 on 60. We talked about independent events, that's where it comes from. Let's try, I'm just trying to do, all right, this one. I want you guys to have to go with this one. Use a tree diagram if it helps you. I like to use tree diagrams to help me. But in this case here, you've got a problem. You've got the town, probability it rains on any Monday is 20%. If it rains on a Monday, so now they're giving you a condition. If it rains on a Monday, then the chances of it raining on a Tuesday is 83%. So this is already telling you it has to rain on a Monday for Tuesday to have 83%. If it does not rain on Monday, then the chances of it raining on a Tuesday is now 30%. You already know this is not independent events because a real Tuesday raining really depends on Monday. Okay, so your job is to draw that tree diagram, fill out the probabilities, and I want you to find the probability that it rains on both days. So what's the chances of it raining on Monday and Tuesday? Okay, and then I want you to find what's the chance of it raining on Tuesday. Okay, let me go with this one, and I'll show you the answers to it. You would go to calculus, say tangent. Let's say I want to find the tangent line of x squared minus 1. So that's my equation. Then comma, capital where the tangent line of the needle is. Let's say I use x comma. Well, that's the same thing for home. You're smiling, Richie. I'm assuming you got the answer. That's why it's too easy for you. Oh, is that why you're smiling? So if I see you in a second, you're smiling, I know why. But if you have a serious face, I'm like, he's got it. Gotta keep looking at your face, man. I'll Putting out a tree diagram in case you need a starter. M stands for Monday rains. M dash means that it doesn't rain on Monday. And I've just followed what they've told me. Tuesday given Monday means that Tuesday rains. Given that Monday did rain, it's 83%. So that means the last 17% has to be Tuesday doesn't rain, but Monday did rain. So I'm just following with that. Once you got the tree diagram, the question is, what does it mean when they say find the probability that it rains on both days? I want Monday to rain, and I also want Tuesday to rain. What am I talking about there? And then how's that different to B? Yes, Aaron. Yep.
You know the formula, raining on Tuesday, given that it rains on Monday, is like the intersection between Monday, Tuesday raining over Monday raining?
Yep.
What's the intersection between Monday and Tuesday raining?
Well, that's what you're looking for. That's pretty much what you just said. So you just told me probability of Tuesday given Monday is equal to probability of Tuesday intersection Monday, yeah? Over the probability, because it's depending on M, so it's probability of M, right? Now, we already got a few things here. You're asking me, what is this? That's what you're asking me. You're saying, what's the intersection? Yeah? And that's precisely what the question's asking. They're saying, what is the probability that it rains on both days? See, when you say probability, T and M, that basically means what's the chances of Tuesday raining and Monday raining?
I think I'm just being confused with the intersection. It's like how can they...
Together is the intersection. This branch specifically is the given. So this second branch here is not the intersection. A lot of students think this is the intersection, but it's not. This is the probability of T given M. So that's the given probability. That's the given part. So technically, if I rearranged all that, this is actually 0.83 is equal to, I don't know, divided by 0.21. So if you want to find the intersection, what's the chances of Tuesday and Monday raining? This is where it comes about, where you're multiplying, whoops, not in red, in yellow, you're multiplying those branches. Because that's what you want. You want the chance of Monday raining, 21%, times with the chance of Tuesday raining, but this is Tuesday given than Monday. It's a dependent branch. So that branch right there is 0.83. So together, you'll find the chance of Monday and Tuesday raining. Okay, whereas it's Monday raining, but Tuesday not. Monday not, Tuesday. So this is the only one that has both days raining. Okay, so if you multiply those two together, well, you rearrange the equation, you would get x is equal to 0.83 times 0.21. Wow. There we go. And whatever that equals to. Where's my Kaz?
It equals to 17.
Is it equal to 17?
Yeah, 17.4. I mean...
Let's find out. 0.83 times 0.21. Yes. Therefore, x equals to 0.1743, which means that the chances of Tuesday and Monday raining is about 17.4%. Leave it in decimals. Sorry? Yeah. Leave it in decimals. Usually, when you're doing probability in the exam, they'll say round to the 4 decimal places. 4 to 5. Yeah, that's why in your calculator settings, make sure your float accommodates for that. Usually, float 6 onwards is a good idea. But Miss Fidelli normally told me the more the better. Okay, it's up to you guys. Yeah. So that's how you do the first one. Both days would be 17 or 0.1743. How do you do on Tuesdays? Raining on Tuesdays only. I just want Tuesday to rain. What's the chance of Tuesday raining? How do I find that one out? Yes, Ben. Good?
No.
Not that one?
No, not sure. Don't you times them and add the Monday not raining and Tuesday raining?
Very good. So these are the two which you were right, but you were missing the 0.79 because 0.3 is just this second branch here. You still need the chances of Monday not raining. Sorry? Was that what you said? I thought you said 0.713, 1743, and did you say times that to 0.3?
No.
What would you say? Oh, you're telling me the answer.
No, the 0.79 times 4.
Oh, is that, sorry. I misunderstood what you were saying. Yes, you're right. Yes, you're right. So there are two branches, and when you say Tuesday raining, out of all the options that you have, the only time Tuesday is going to rain is here. Yeah. So you want to know the total probability, then add these two. That gives you the overall probability of it raining on a Tuesday. So here we've already got the first part. We already knew it was 0.1743. You just need to add on this branch, which is then 0.79 times 0.3. Add that on with your previous answer. That tells you the probability for Tuesday. Does that make sense? Yeah? Because that's what 13B is about. So that's literally all you're practicing. Now, the only times it gets tricky is when you're playing around with the formula. They give you bits and pieces. But that essentially, right there, that's a question that does conditional probability. Okay? So, I'm just going to show the answers here. This is a Carnot map. You don't have to use a Carnot map. I did it just so it makes it look easier for you, for some of you who like Carnot maps. Okay, so I did Monday raining, Monday not raining, Tuesday not raining, and our goal is to find intersection of both, okay, or you're going to find Tuesday only, so which means this section over here. Okay, cool. Here we go. Oh, that's a good question, but before we get back to that, I'm just going to take a step back. I want you to try 10 for me. 10. I want you to do 10A, B, and C. So if A and B are independent events, such that PRA equals 0.5 and PR of B, so the chance of B is 0.4, what's this equal to? On a logical basis. What is A equal to? They are independent events. What is probability of A given B equal to? Yes, Trent.
So the difference between mutually exclusive and can independent events be accepted?
Yes.
Yes. So how can you do B?
Wait, did you say can they be independent and intersect? Yeah.
Okay, so how do you know B? Because it says the intersection between them, you don't know the intersection.
But you can find the intersection. The theory. So if I were to draw out the tree diagram, we have, you either get A, you don't get A. You get B, you don't get B. You get B, you don't get B. Now because they're independent events, it is not B given A anymore, because B given A doesn't exist. True? Because when they're independent, we're saying the chances of B depending on A is actually just the same as probability of B. That's what independent events means. Yeah, it doesn't depend on A. So that means right here I can rub off this section here. Now if I want to find what's the chances of A given B, the answer, A given B is just saying what's the chances of getting A? Because B doesn't affect it. So this is just 0.5 on a logical basis. If you would answer the intersection of A and B, you're really saying what's the chances of getting A and then also getting B? This is chances of getting A, which is 0.5, and getting B. So you're multiplying the branches just like we did before. In this case here, it would be, where is it again? I'll do it in red. They said this is 0.5 and this is 0.4. So that means chances of A intersection B has to be 0.5 times 0.4, which is 0.2, is it? Okay. 0.2. And then A union B. A union B, like I said, every time you see a union, you should be thinking of yes, you plus them together. The addition rule. The addition rule, which is probability of A union B, which is equivalent to probability of A plus probability of B. Subtract the intersection between them. Now you got every piece of information given, 0.5, plus 0.4, take away 0.2, so the answer has to be 0.7. Okay, so that's what I mean by the difference is really understanding, because the hardest part of this is not B and C, okay? It's not B and C, it's actually A. A is the first step. A is the concept that you need to understand that when we say independent events, B doesn't depend on A, so therefore it's just the same thing as saying getting B. So when you look back at this, chance of getting A, given B, well, B doesn't affect it. They're independent. So that means it's just the same thing as getting A. Once you get that around your head, then drawing the tree diagram makes a lot of sense. A, B, or A dash, B, B dash, B, B dash, A intersection B, A intersection B. Okay? How do we feel with that? That's 13B. Pretty good? All right, I'm going to leave you guys there. So that's 13B. If you want to have a go with this question here, which I'll select it, is a pretty cool question. 2014, pretty recent. So it's in exam 1, question 9. Remember I said the last 2 questions are the hard ones. Those are the ones where it gets you thinking. You have enough skill at this point to do that question. Okay, but it requires thinking. And it requires you to decipher what the question's asking. Okay, because if you get the question, then answering is easy. When you don't get the question, you don't know your theory well, then answering this will be very tricky. The hardest part here is forming your events. Get your sets right, get your events right, then answer the questions right. Because right here, the examiners have purposely made it feel like there are too many events to deal with. You get the correct events, deal with it, then it makes a lot of sense. Okay? Have a go with this one, and I'll leave it there. But I'll pause the video, and the next slides will tell you the answers.